So it's a pleasure to introduce our second speaker for this afternoon session, Bjorn Poonen from MIT. He's known for his broad, highly original and sustained contributions to many parts of number theory over several decades. And today he'll speak to us on heuristics for the arithmetic of elliptic curves.
Okay, thank you very much. So let me start by, well, I'm not going to list, all these co-authors. I mean, there are just too many of them to say their names, all of them. But so this was not just one big joint paper. It was not with all, I mean, if you had all these authors, I could probably prove almost anything. But it was a series of papers where I worked with some subsets of them, a few at a time. So, okay, so this is about elliptic curves. So let me just first remind you what an elliptic curve is. So we're going to be talking about elliptic curves over Q, and each one of those has an equation, y squared equals x cubed plus ax plus b. It's a projective closure of such a curve, where a and b are rational numbers, but you can scale the variables, and you can arrange for a and b to be integers, and if you scale them just right, you can arrange, there's a unique scaling of them that makes it so that there's no prime p such that p the fourth divides a and p the sixth divides b. And, well, there's also the 4a cubed, that discriminant being non-zero. That's just the smoothness condition. Okay, so for now, I'm going to consider only the elliptic curves in this special form. So so E is going to be the set of such curves. So E has one elliptic curve from each isomorphism class over Q. And once you put E in that form, you can define a naive height of the elliptic curve just in terms of the defining coefficients as this combination of A and B. And then you can look at the elliptic curves of height up to a certain bound, and that'll be some finite subset of elliptic curves that eventually exhausts all the elliptic curves as h grows. And you can quantify how quickly it exhausts the curves. You can count how many elliptic curves there are up to height h, just because it's essentially what you have to do to prove this proposition here is just to count how many possibilities there are for A. A can go up to about h to the 1/3, and B can go up to about h to the 1/2. And then, well, there are these conditions, but that just these sieving conditions, but that just changes the constant. So the number is about h to the 5/6, and this is going to come up later. Okay, but what we're interested in about these curves is their rational points. And the first theorem, as you probably all know, is Mordell's theorem that the set of rational points is first, it's an abelian group, but what Mordell proved is that this abelian group is finitely generated. And so, well, then you know that it has this structure. It's going to be some direct sum of a free group and a finite abelian group. And so now the question is to understand what are the possibilities for this rank R and this torsion subgroup T. And the torsion subgroup is completely understood, thanks to Mazur. So there's just a finite list of groups that can occur. And so, okay, so let's move on. Let's figure out the rank. So what are the possibilities for the rank? And this is a very old question. In fact, the question about what the rank could be came even before Mordell proved that rank made sense. So it was, Poincare was already asking what the rank could be. And so he asked, and implicit in his question is the question about whether the rank can be arbitrarily large. Can you find elliptic curves of higher and higher rank? And that's the main question that I want to address today. So is the rank bounded as E varies? And if you look back in the history, then it seems that early authors conjectured that it should be bounded. So Néron, who is one of the first people to construct elliptic curves of rank of relatively high rank, 9, 10, 11, he conjectured that actually there should be a bound, maybe because he was having difficulty going beyond that. And then Honda also, but then Castle said something like, pretty much everybody's saying that the rank should be bounded, but I think it's not bounded. So he said he had some reason saying that, well, you have to, for the rank to get large, the conductor has to be sufficiently large, and people just hadn't searched that far yet. And after that, it seemed, I don't know if they were thinking independently, but anyway, everybody seemed to say, it seemed that there was a consensus that it should be unbounded. With a few exceptions, there's an article of Rubin and Silverberg where they have some heuristic based on equidistribution of certain lattices, and that would predict, if you believe that, then their argument would predict that if you look at a family of quadratic twists, so these are just so maybe these are just elliptic curves where you put an extra integer in front of the equation. Then within that subset of elliptic curves, the rank should be bounded by 8. But they didn't use this to actually conjecture boundedness because this is actually false. I mean, there are elliptic curves of rank greater than 8, and so they didn't. I guess they weren't quite sure what to make of that. And another heuristic was due to Granville. He came up with it around in the mid. Well, I don't know how you pronounce it. The mid-O's. I don't know how you pronounce that decade. But anyway, in the middle of that decade, he came up with this heuristic, and he didn't publish it, but eventually got published many years later. And there was another heuristic based on counting integer solutions on the total space of a family of elliptic curves. And some naive heuristics for that, just sort of analogous to, well, just based on things like the probability that an integer is 0 is roughly 1 over the size of that integer. But heuristics like that would predict that you would have only finally many in a family of quadratic twists, you'd only have finally many of rank greater than 7. And Watkins adapted that, used Granville's heuristic in the context of the family of all elliptic curves, and he found that in the family of all elliptic curves, there should only be finally many elliptic curves of rank greater than 21. So what I want to do today is give another heuristic that, well, sort of miraculously gives the same number 21 as being an upper bound for the rank with finitely many exceptions. But what makes this different from previous heuristics, well, first of all, it's not based on any of these ideas, but instead it's based on trying to model not just ranks, but also some other associated groups like Selmer groups and Shafarevich-Tate groups, and try to get a model for the complete package of all these things. And the advantage of doing that is that then you can try to corroborate this model by checking it against theorems that are actually proved about Selmer groups and Shafarevich-Tate groups. All right, so I'm not going to define Selmer group or Shafarevich-Tate group. I mean, they're defined using Galois cohomology, and, well, you either know it or else I'm not going to teach you it right now. But the good news is you don't really need to know what they are to understand what I'm going to say. So anyway, it's just the n for each integer n, there's an n Selmer group, and the point of it is that it gives you an upper bound for this quotient group. And because of that, you can use this to, if you know the n Selmer group, that gives you an upper bound on the rank. In fact, this is pretty much the only known way of getting upper bounds on the rank of the group of rational points. Yeah, and then so this is an upper bound, and then there's this n torsion in the Shafarevich-Tate group that measures sort of the error in this upper bound. It measures the failure of this upper bound to match what this group is trying to approximate. So we kind of wish that weren't there on the right-hand side, but okay. Anyway, so what you can do is you can let n run through powers of a fixed prime p, and that way you can get better and better, at least potentially better and better upper bounds on the rank. And if you can take a direct limit and package all these groups together and get this exact sequence where you have the p the infinity Selmer group in the middle, which by definition is just the direct limit of the n Selmer groups. And then you have, well, this group that will be isomorphic to qp mod zp raised to the r, where r is the rank. And then on the right, you'll have the p primary part of the Tate-Shafarevich group, which is conjecturally a finite group. So, I mean, if you believe that, then once you know the p the infinity Selmer group, then you know the rank, because you just look at how many copies of qp mod zp there are in there, and then what's left over is finite. Okay, so our goal is then to have a model for all of these sequences to try to predict what the distribution of these groups are as E varies over all the elliptic curves over Q. So I'm going to start with the Selmer groups, just the finite Selmer group. In fact, I'm just going to do the P Selmer group where P is a prime for now. So, and well, it's known to be a finite group. This P Selmer is, in fact, is a finite dimensional FP vector space. So the only question is, what is its dimension? And so well, we're hoping to get a certain distribution over the possible dimensions. There should be some probability that this is a zero-dimensional vector space, some probability that it's dimension 1, some probability that it's dimension 2, and so on. So we want to know what is this distribution? And what we're going to do is I'm going to describe a linear algebra process that conjecturally gives the same distribution as the p-summer group of an elliptic curve. And so here it is. So start with a 2n dimensional vector space over fp, so this, and equip it with this sort of standard hyperbolic quadratic form that on this 2n vector gives you this output. Then with respect to, that also gives you an inner product on the vector space in the usual way. You go from quadratic forms to symmetric bilinear forms. So you can talk about the perp space of a subspace. And a subspace of this 2n dimensional vector space will be called maximal isotropic if, first of all, the quadratic form vanishes identically on that subspace, and also it should be equal to its own perp. So you can't put in another vector or take a direct sum with another one-dimensional space to make it bigger. Okay, so well, there are only finally many of these things because all of this is happening inside a finite-dimensional vector space, and so you can imagine choosing the z at random. You can choose a maximal among all of the maximal isotropic subspaces. In fact, you can choose 2 of them at random too, and then each of those will be half of the dimension. That's the way maximal isotropic subspaces work. But if you intersect them, then there are various possibilities for the dimension of that intersection. And it turns out that if you take the distribution of the dimension of that intersection, and then take the limit as the ambient space dimension goes to infinity, it converges to some distribution over finite dimensional vector spaces. And that is the conjecture for what the Selmer group should look like. Now, why should you believe anything like this? I just made up this linear algebra, this process. Why should this have anything to do with Selmer groups? Well, I'm not really going to tell you, but I'll tell you. Okay, I'll give you some evidence. So, okay, this is just a copy of the conjecture I had on the previous slide, and you can actually analyze this linear algebra process to figure out what the probability is of each dimension, and this is the formula for it. So this is something that decays as S. If you want to know what's the probability that the Selmer group is 17-dimensional, you just take S equals 17, and then this product will give it to you. Now, why should you believe that this is the right formula? So one reason is that this is actually proved for p equals 2 not for the family of all elliptic curves, but for a family of quadratic twists, certain families of quadratic twists. So the first person to do that was Heath Brown back in 1994, and then other people have generalized it to other quadratic twist families. And in fact, actually, I've presented this sort of in backwards historically. Heath Brown was first. He found this distribution as being coming from the 2 Selmer group of elliptic curves, and then Eric Rains and I looked at this formula and we said, okay, what linear algebra process can we think of that will give that formula? And we just tried all the things we could think of, like intersecting, like random quotients of anything you could do in linear algebra until we found one that matched that formula. And then we said, oh, that must be it. And once we did that, we actually also reversed engineered and found that actually the Selmer group is an intersection of 2 maximal isotropic subspaces in some big cohomology group. So that's further evidence that maybe it should be modeled by if it is an intersection of 2 maximal isotropic subgroups, maybe it's reasonable to model it as an intersection of 2 maximal isotropic subgroups. Then the only question is, are they really random? And finally, this conjecture, once you know the distribution of this dimension, you can calculate other statistics, such as the average size of the Selmer group, or the size of the average of the square of the size, and things like this. And at least it's known that this conjecture is compatible with all the theorems that Bhargava and Shankar have proved about average Selmer group size. So far, it seems to be compatible with everything that's actually a theorem. And so this seems to be a good reason to believe this. Okay, but this is not, as I mentioned earlier, this is just an upper bound for the rank. So this is not going to tell you directly what the rank, how the rank of an elliptic curve can behave. So to get a better idea, we'll look not just at the p-Selmer group, but also the p-squared Selmer group and the p-cubed Selmer group. And there's an analogous linear algebra model that will predict what the distribution of those are. And you can even take the limit and make a model for the p-infinity Selmer group. So this is what I did with Manjul Bhargava, Daniel Kane, Hendrik Lenstra, and Eric Rains. So we formulated a conjecture for the p to the e, for the p to the e Selmer group for each e, and then we packaged them together, and we managed to find one model that would give you the p to the e, the p to the infinity Selmer group. And once you have that, then you can also see what the infinitely divisible part is, and then the quotient, which should be the Shah. And so that led to a conjecture. And so this should tell you what the distribution of the rank is, because once you know what this is, it's just how many QP mod ZPs there are in here. And so we have then a conjecture for how rank should be distributed. And not only that, we also have a conjecture for how the Shaffer-Average Tate group, the P primary part of that, should be distributed. And in fact, so we have this, and we can do it. We can even condition on the rank of the elliptic curve and get a distribution here. And that seems to be a good idea to do. And you should believe this too, because this has also been, well, at least in a quadratic twist family, this has been proved for p equals 2 recently by Alexander Smith. So there seems to be good evidence for this as well. All right, so now I want to focus in on this particular statement about predicting the distribution of this group, and this is how we're going to get a handle on the rank. So I want to say we're not the first people to predict a distribution for how Shaffer-Average Tate groups are distributed. The first was Delahaye in 2000 and his author, or 2001, and and later his co-author. And so they had a heuristic analogous to the Cohen-Lenstra heuristics for class groups. Where they predict the exact probability of each group appearing as oops, sorry, what did I do? Yeah, okay. As this group. And and there's actually a third distribution that's also a third prediction that I and my co-authors made. That's what I'm outlining here. And one thing that we prove is that those three distributions, there are three different conjectures for this, what the distribution should be. We at least prove that they are compatible with each other. So, as I like to say, we might be wrong, but if we're wrong, then we're taking other people down with us. So what's this third linear algebra construction that gives you the distribution of this Shaffer-Average Tate group? So here's what you do. You start with the p-adic numbers, the p-adic integers, and you look at integers, n by n matrices with p-adic integer entries, and you take the ones that are skew symmetric, alternating. So transpose should equal minus a. Okay, so that's some space of matrices, and if you have such a matrix, you can view it as a linear transformation from a rank n ZP module to another one, and you can look at its kernel and co-kernel. So the kernel will be some free ZP module, and the co-kernel will be some finitely generated ZP module. And now if you want to model rank R elliptic curves, it turns out that what gives you the right distribution is to sample from the matrices whose kernel has rank R, if you're looking for rank R elliptic curves. So that's some space, it's some subvariety, and you can talk about some p-adic measure on that subvariety and sample a matrix from that, and then look at the co-kernel and take the torsion submodule of that. So, and because its co-kernel is finally generated, this is going to be some finite abelian p group, and the conjecture is that the distribution of this, at least asymptotically as n goes to infinity, the distribution of this is supposed to be what models the Shaffer-Average Tate group. Okay, so now here what I'd like you to focus on, is this condition that in order to get the model for the Shaffer-Average Tate group for rank R elliptic curves, what you do is you condition on this. You condition on the kernel having rank R, or if you talk about the rank of the matrix, that's the complementary. That would be n minus R then. Okay, so this is a clue as to how rank should be modeled. So this is just recalling what's on the previous slide. If you condition on this, if you condition on the rank of the kernel being R, that should give you the distribution of Shah, or for rank R curves. So what's the simplest explanation for this? What would be the simplest possible explanation? Well, maybe if you don't condition on this, and you just look at if you just choose A at random, and you just look at what possible ranks of kernels come out, maybe that should be the distribution for the actual rank of elliptic curves. So that would be the simplest explanation for why this is giving you the distribution for rank R curves. So, okay, so if you accept that, what does that tell you about ranks of elliptic curves? And it tells you something, but maybe not enough, maybe not what you'd like to know. Here's what actually comes out. I mean, what do you expect if you take a random matrix and you take its kernel over ZP? What do you expect the kernel to be? I mean, it's an n by n matrix. I mean, if the determinant is non-zero, well, that means the kernel is 0. And you might say, oh, most of the time, if I choose a matrix at random, the determinant will be non-zero. So most of the time, the kernel should be 0, have rank 0. And that's true, except for the fact that this A is an alternating matrix. And because of it being an alternating matrix, that constrains the rank of the matrix to be even, which is complementary to this. And that constrains the parity. So you can't actually always have, I mean, so if n is odd, an n by n alternating matrix always has determinant 0. So, okay, but other than that, you expect the rank of this kernel to be as small as possible, as small as is compatible with the parity. So if n is even, then usually the determinant is probably non-zero. In fact, you have to avoid, I mean, it's only on a hypersurface in the space of matrices where the determinant is actually 0. And so if you choose something at random, with probability 0, you're going to miss that hyperspace, and you'll get the smallest possible kernel. Yeah, and this is compatible with what people expect for elliptic curves. So there's the Goldfeld conjecture, which actually he made in the context of quadratic twist families and analytic rank. But anyway, so there seems to be good reasons to believe that this is the truth for elliptic curves. So, well, if you imagine n is sort of random, then 50% of the time the rank should be 0, and 50% of the time the rank should be 1. But that doesn't really tell you what you want to know, because I really want to know what's happening in these 0%. I mean, I don't want to just know that they're asymptotically 0% have rank more than 2. I want to know really how many. I mean, are there any of rank 29 or whatever? Yeah. So, sorry, you had 37. Yeah, I would like. Well, he would like to know: are there infinitely many, or are there elliptic curves of rank 37? And well, this is not going to tell you that. It'll just tell you that 0% of elliptic curves have rank 37, which seems likely. But we need a finer analysis in order to figure out how 0% is this? I mean, how is it? Is it really 0, or is it like something that's asymptotically 0? Okay, so to do this, we're going to modify the model. Instead of looking at the rank of a p-adic matrix, I'm going to look at an integer matrix. I'm going to sample A from integer alternating matrices. And not just all and they're going to be integer matrices where the entries have a certain size. And the size of those entries is going to be determined by the elliptic curve I'm trying to model. And it'll be some function of the height. And so what's the advantage of this? I mean, if I take an elliptic curve, if I take a matrix where it's integer entries and the entries are bounded, now there's some small but positive probability that the determinant is 0, or that it lands on this particular hypersurface. And so although asymptotically, if you let the integer size go to infinity, then the probability of having determinant 0 gets smaller and smaller. It tends to 0. But you can quantify how quickly it goes to 0. And so for a given height, you can ask, if you know how big these entries are, you can say, what is the small probability of having this particularly of this determinant being 0? In other words, of getting higher rank. And so yeah, so that's the point of this. And so, well, and we also eventually want to let n grow as well, the size of the n by n matrix, the size of the matrices. So, okay, so we will want a model in which we're going to look at co-kernels of integer matrices now. And the matrices are getting bigger and bigger, and the entries are getting bigger and bigger, and all this is happening as the height of the elliptic curve being modeled grows. So, okay, so what is the actual model? Okay, so here's the model. So if you want to model an elliptic curve of height h, and that was just then, well, using these growing functions that I'm going to talk about later, you choose a large integer, so this is going to be the size of the matrices. Choose it about this, and a random parity, since I don't want bias in the parity, and then choose a random integer matrix associated to this elliptic curve, and of entry size bounded by this other function. And I do this. I'll do this independently for each elliptic curve. It's going to be something like the Kramer model for prime numbers, where you can, if you want to model the prime numbers, one naive way to do it is you say, okay, each integer is going to be, I'll declare that 2 is prime with a certain probability, 3 is prime with a probability, and so on, and x is prime with probably 1 over log x. And if you just sample all those, you get some sequence that looks kind of like the primes. And so I'm going to do something similar here. For each elliptic curve, I'm going to sample a random matrix, and out of that matrix, I'm going to build something that's supposed to be like a substitute for the rank. So I take this random matrix, and I take the torsion subgroup of the co-kernel. That's the pseudo, it's sort of this fake Schaffer average Tate group. And then I also get a pseudo rank by taking the rank of the kernel. And so the question is, how do these things behave as E varies now? And these are supposed to model the actual Schaffer average Tate group and the actual elliptic curve, actual rank of the elliptic curve. Okay, and I mean, this is not complete. This model is not complete because I haven't told you what these growing functions are. But you can figure out what they should be because there are some theorems that are known about how the Schaffer average Tate group grows in a family, for example, in the family of rank 0 curves. There are theorems you can prove, conditional on standard conjectures, like the generalized Riemann hypothesis and so things like this. So you can actually analyze what the average size of this should be, and based on that, you can figure out how quickly this x to the eta should grow. And so it turns out that this is the right rate of growth. So x to the eta, it doesn't really matter so much what x and eta are as far as this goes, but this exponentiation should grow like h to the 1/12. Okay, so at this point we have a model. So now we list all the elliptic curves. We do this random matrix for each elliptic curve. We get this sequence of things that should be behaving like the ranks of all these elliptic curves. And we can ask what happens if we do this random experiment. What ranks come out? And so we prove a theorem about that. So this is unconditional theorem. So with probability 1, when you do this experiment, you can ask how do these pseudo ranks behave? Well, you can ask how many elliptic curves up to a given height have a given rank. And well, if you look at all elliptic curves, that was h to the 5/6, which is the same as h to the 20 over 24. And it turns out that every time you try to increase the rank beyond 1, we prove that the probability of, or at least, sorry, the number of elliptic curves of, well, yeah, I can say in terms of probability. Each time you increase the rank beyond 1, the probability of having that higher rank goes down by a factor of h to the 1/24. And, well, you can kind of see where this is going. And eventually you get down to a situation where you expect, well, here I guess it's too close to call, but beyond 21, you expect that there should only be finally many elliptic curves even if you let h go to infinity, you get some. If you sum over all h, you'll get some geometric series that converges, and and this is probability 1. So it's got to be true. The only problem is that it's not saying anything about actual ranks of elliptic curves. It's saying things about these pseudo ranks that are formed only out of linear algebra. But if you believe that linear algebra construction is actually modeling elliptic curves, then this should be the truth. And you can compare this against how, what actually happens for the actual elliptic curves over Q. I mean, is it true that there are only finitely many elliptic curves of rank greater than 21? Well, it's kind of close. I mean, Noam Elkies did some computer searches, and he found that there are infinitely many elliptic curves of rank at least 19. So, but fortunately, that's not a contradiction. That doesn't contradict our model yet. It's getting kind of, it's a little bit dangerous, but it's okay. I mean, also he found one elliptic curve of rank at least 28. But that also, I mean, nobody said that there weren't any elliptic curves of rank greater than 21. I just said that there would be only finitely many. So that's also consistent with that. So far everything is consistent. And you can also ask other questions. So let me move on to this other slide. So instead of looking at the family of all elliptic curves, you could fix a particular torsion subgroup. Remember I told you that there's this list that Mazur had of all the possibilities for the torsion subgroup. And so you can stratify it. You can sort of separate the count out according to the torsion subgroup. And if you do this, so for example, if you look at all the elliptic curves whose torsion subgroup is Z mod 6Z, they're not h to the 5/6 anymore. They're more like approximately h to the 1/6 of those elliptic curves. You can use the same model for the probability of having a certain rank. I mean, the only difference is that you don't have as many elliptic curves. You're looking at a sparse set of elliptic curves. So the height, if you list them, the height is going to go to infinity faster. So the probability of having high rank will decay faster. And so using this, you can prove. Well, within our model, you can see what our model would predict, and it gives you a bound, that beyond which there should be only finitely many elliptic curves. So for Z mod 6Z, in our model, there are only finitely many elliptic curves whose pseudo rank is greater than 5. And for each one, each of these entries gives you a test that you can do against. You can do a test against reality. So this last column is the reality column. So on the other hand, I mean, other people have been doing searches. People have been looking for elliptic curves with torsion subgroup Z mod 6Z of high rank. And the best they've been able to do is to find infinitely many of rank 5, which matches exactly what our bound says, which is, again, kind of dangerous, but I mean, it looks good, though. Because the known examples are always below or equal to the actual bound that we say should happen. And it's not as if and it looks kind of close too. So, I mean, it looks as if, well, I don't know. I mean, to me, it looks as if we must be doing something right. I mean, for this to be, well, anyway, you can judge for yourself. So, all right. All right, so let me now move on to the question of what happens. I mean, so far I've been talking about elliptic curves over Q, but you could also ask about elliptic curves over number fields or global function fields. And you can ask, okay, what happens to the heuristics over those kinds of fields? So let K be such a field, either a number field or a global function field over a finite field. And you can single out a set of representatives for the isomorphism classes, so of elliptic curves over that field. So let's call that E sub K. And you can define an analog of this number beyond which there should be only finitely many elliptic curves of that rank. So you can list the elliptic curves, the ranks of all the elliptic curves, and take the lim sup, which is that's the number beyond which there should be only finitely many with greater rank. Okay, so our heuristic applied to Q predicts that this lim sup should be either 20 or 21. I mean, 20 was too close to call, but so anyway, so I wasn't quite sure what was happening. That was where it was h to the O of 1, and I don't know whether that little O of 1 is positive or negative, so I don't want to say what that should be. Well, I mean, if you take our heuristic naively, you can redo the same calculations. You can figure out what the average size of the Shaffer-Tate group is, and you can calibrate it using that again. And it turns out that if you do that, you get exactly the same answer. That this number beyond which you should have only finitely many elliptic curves of that rank is again 20 or 21, and it should, independent of what the number field is. Okay, so how does this compare with reality? Well, not so well. So what's the truth now? Okay, so this is the heuristics. Now now this is reality. What actually happens? So over function fields, you actually can have elliptic curves of higher and higher rank. I mean, it's still, for any given elliptic curve, it's finely generated, but the rank can be arbitrarily large. So this has been known for a long time. In fact, this is one of the reasons that all those people were on the earlier slide were conjecturing that the same thing should happen over Q. But on the other hand, these constructions are very special. They involve the Frobenius, and they use, well, I'll say a little more about this on the next slide. But yeah, so okay, so there's definitely something wrong with global function fields. How about number fields? Well, there also things can go, it doesn't quite match up. If you vary the number field, you can prove, we prove that this number can be arbitrarily large. So, but it still might be true that for any fixed number field, there is a bound on the rank. But that bound will have to grow as you vary the number field. Because we prove in two different ways that this lim sup can grow for certain special number fields. So you can either use number fields inside anticyclotomic towers and construct elliptic curves of high rank by using Heegner points, or you can do another construction where you just take the number field where you start with Q and you join a bunch of square roots to Q to get a multi-quadratic field. And over such fields, over certain fields of that type, also you can prove unconditionally that you can find elliptic curves of high rank and infinitely. Yes. So the question is, what happens if you restrict to elliptic curves that are not isogenous to any of their Galois conjugates over K? Well, I haven't thought about that question, but maybe if there's time at the end, we can talk more about that. Okay, so, all right, so here's, okay, how do we reconcile the heuristics and the truth? I mean, the heuristic was obviously, the heuristic was saying 20 or 21, but the truth was saying it's infinite for function fields and something possibly bigger than 21, possibly a lot bigger than 21 for number fields. Yeah, so I mean, yeah, going back here, so I mean, this is saying that I can show you a number field for which there are infinitely many elliptic curves over that number field of rank greater than 1,000. I can write one down for you. Okay, so that's not good for the heuristic. But what's special about the elliptic curves that are used to prove, the elliptic curves of high rank that are used in those proofs, they're always elliptic curves that actually come from a subfield of the number field or global function fields. So what you do is you start with an elliptic curve over Q, and you say, okay, over this big anticyclotomic field, over that field, I mean, the elliptic curve is really defined over Q, but it's only over the field extension that acquires high rank. So maybe you should, so our proposal to fix this is to exclude all such curves. If you want to study elliptic curves over a number field K, you really should take elliptic curves that are really defined over K. You shouldn't be taking elliptic curves that come from some smaller field. And if you do exclude all those, then it's conceivable that, so if you do that, you just take the elliptic curves that are not base changed from a subfield, and you redefine the lim sup to count only those, then it's still possible that this is always finite, even for function fields. And it's not quite, it's still not, I mean, it doesn't fix everything. It's still not quite true that this is always going to be 21. We can prove, I mean, using an example of Scioto, that for at least for certain number fields, this bound has to be at least 68. But it's at least conceivable that it could still be finite. Okay, so, all right, so maybe the last thing I will talk about is, so all this was for elliptic curves. What happens if you look at higher dimensional abelian varieties? Well, I guess you could look at lower dimensional abelian varieties too, but I think we know what happens then. Okay, so, all right, so here you'd want to fix. Not only, well, here you should fix the dimension. Otherwise, you could take an elliptic curve, elliptic curve cross itself a million times. And of course, that can have rank 1,000,000 or higher. So we'll fix the dimension, and we'll fix the degree of a number field. And we can ask, is there a bound for the rank of the group of rational points that depends only on the dimension and the degree of the number field? I mean, we know, I mean, the Mordell-Weil theorem tells you that at least it's true that A of k is still a finely generated group. It still has some rank for any given A. The only question is it uniformly bounded? And, well, I mean, we can start to try to answer that question. I mean, the heuristics are less strong. I mean, I'm probably not, well, even if you were convinced by the previous one, you might not be convinced by this, but at least there's some hope that, at least, well, okay, let me just say, well, I personally believe that it's still uniformly bounded, and here are some reasons why you might believe that. So if you fix the dimension, which I'll call G, then you can use, well, by doing restriction of scalars from K down to Q, you can reduce the problem of doing abelian varieties over Q, and also by using Zarhin's trick, which replaces the abelian variety A by A to the fourth cross A dual to the fourth, you can reduce to the case of studying principally polarized abelian varieties over Q. And the advantage of doing that is that they fit into one algebraic family. So you can write down one algebraic family that includes all the abelian varieties involved in one instance of this problem. And you can ask, and so now it's just a question of in this algebraic family of abelian varieties, can you bound the rank? And you can try to do what we did for elliptic curves. You can define some kind of naive height by looking at the equations defining these abelian varieties, say as in the work of Mumford. You can write down some explicit equations for these, and then you can define the height in terms of those defining coefficients. And you can prove then for such a family, the number of abelian varieties of height up to h, well, it's not going to be h to the 5/6 anymore, but it'll be h to some finite number. And so it'll be some polynomial in h is for the bound. And so, well, okay, here's the big if. If you believe that there's some linear algebra model involving some sort of pseudo-rank, such that the probability of having of the rank of the abelian variety going up by 1, the probability drops by some fractional power of h, like the h to the 1/24th for elliptic curves. If you believe something analogous to that, then the same analysis we did before will predict that the pseudo-ranks are bounded. And then, well, if you also believe that pseudo-ranks have something to do with actual ranks, then you should also believe that the actual ranks should be bounded. So yeah, so I guess yes, yeah, it should be bounded. All right, so that's okay. So that's pretty much it. So let me now just end in my last 3 minutes by summarizing what just happened in this last 45 minutes. So we had heuristics for Selmer groups, and that led to a model that for the whole package, not just for Selmer groups, but also predicted Selmer groups, Shaffer-Average-Tate groups, and ranks all together. And several aspects of the model are supported by actual theorems. So there are reasons to believe that the model is correct. At least it's correct. At least it's compatible with the things that have been proved so far. And in that model predicts that the ranks that come out of that model are bounded by 21, with finally many exceptions. So if you believe that these heuristics are correct, then this suggests that the rank should be uniformly bounded as the elliptic curve varies over all elliptic curves over Q. And as I explained on the last few slides, there should be similar heuristics for other number fields and global fields, as long as you are careful to avoid these sort of special curves that actually should have been considered that are actually coming from lower fields. So once excluding those, there are reasons. Well, you might believe that they're similar, that they're still a uniform bound. And then finally, as I explained from the previous slide, you might believe also for abelian varieties that it should be bounded in terms of the dimension and the number field or the degree of the number field. Okay, so that's all. So thank you for your attention.
Are there any questions for Bjorn? Yes. Yes.
So when you mentioned at the end abelian varieties, I was thinking it sounds too general, and maybe why not to wonder about Jacobian varieties. Maybe it's just the same, but there are some results about the analytic ranks of Jacobian varieties. I think Kowalski and Ivanek, I don't remember whom, Are those compatible with the results that you would get for the abelian varieties or the statisticals? Or have you, I don't know.
So I don't remember exactly what they prove, but I mean, of course, the Jacobian varieties are included in, in the abelian varieties. So this, well,
because they
so
have
that might be easier to study if you study Jacobian varieties. I guess this is what you're saying, and there's some results.
And they have some results in the analytic rank that will say, like, or maybe the statistical model will say, I mean, if it's compatible.
So I haven't. I'd be happy to hear more about that. I haven't checked with this, but I would. Yeah, but I would assume that they don't get unbounded rank. So
no, they don't.
Okay, good. So okay, so I mean, I mean, I guess I'm predicting something even stronger. That even if you look at all abelian varieties of fixed dimension,
that sounds ambitious.
But yeah.
Okay, thank you.
Anyway, thank you for the question. Oh, they're compatible with Goldfeld's conjecture, 50-50. Okay, so that's okay. So everybody's happy. Everything's compatible. So you should believe everything I said.
Yes, well, I have a question along those lines. So if this is true, then I mean, just to make an obvious point, the number of integer points on an elliptic curve would be tiny. Even with our current state of knowledge, as in bounds of Siegel, explicit bounds on Siegel's theorem, we would have that on an elliptic curve defined by an equation whose coefficients are of size at most n, there could be at most about log n elliptic points. We can double check afterwards. Is this compatible with all existing conjectures?
Well, there's a theorem of Levent-Alperga that proves that if you average over all, maybe you know this, if you average over all elliptic curves over Q, and you count the number of integer points, you average the number of integral points, then that's finite.
Yeah,
so
well,
that's
sure, but that uses a kind of machinery that I'm telling you. That I'm
It's related to what you were, to your question.
So on average, sure, because on average the rank is small.
Yeah, so I think, as far as I know, it's compatible with everything. It's known.
Yeah, but really that there are so very few points on every single elliptic curve?
I think it's okay.
All right.
I think it's...
If you say so.
Can you get anything like the standard Cohen-Lenstra Heuristics by replacing abelian varieties by tori?
Oh, so the question is, can you get something like the standard Cohen-Lenstra Heuristics for class groups using tori instead? I guess I don't know how to answer that precisely, but maybe I could say that the distribution, if you want the distribution of class groups, say the p part of a class group of imaginary quadratic fields for some odd prime p, then that has an analogous linear algebra. You can get that distribution also by a linear algebra construction. So this is an observation of Friedman and Washington and also Ellenberg and Venkatesh that you can get it by taking, again, the torsion subgroups of co-kernels of random integer matrices, except now you don't require the matrices to be alternating. In fact, we are partly inspired by that in developing one of these models here.
Are there any further questions? If not, I'd like to thank Bjorn again for his lecture.